Over the last few lectures, we have recapitulated several important topics in quantum mechanics that you have met before. Now, most of these topics involve the solution of the time-independent Schrödinger equation in some form or the other, and we are dealt primarily with situations where you could find an analytical solution. Now, you must realize that such a situation, although very important, is actually rather rare. Only very few problems in quantum mechanics can really be solved analytically. A vast majority of problems actually involve cases where the equations cannot be solved analytically and you have to resort to various approximation methods. So in this part of the course, we are going to look at various approximation methods that are used in quantum mechanics. We will focus primarily on the use of approximation methods to solve the time-dependent and time-independent Schrödinger equation. We will begin with the simpler case of the time-independent Schrödinger equation first, and there are several methods that could be used in this case. We will focus on the most important ones. Let me also point out that most of these methods had their origins in the study of classical mechanics. So, there are classical mechanical counterparts for most of the methods that we are going to talk about, but we will focus primarily on their application to quantum mechanical systems. The first approximation method that we will talk about is the so-called variational method, which is a very, very important method in quantum mechanics, not only because it allows you to estimate a very important quantity, ground state energy of a system, or sometimes even a few of the higher excited states, but also because it lies at the heart of several important results which in fact are important enough to start off their own topics entirely. Just to illustrate as an example, just to give you an example, one of the most important methods that is used to study complex quantum systems like atoms and molecules or condensed matter systems is the so-called density functional theory. And at the heart of the density functional theory is a theorem which is basically based on the variational principle. We will not really look into those advanced topics here. We will focus primarily on the use of the variational method to estimate ground state and sometimes a few excited state energies for the time-independent Schrödinger equation. The use of the variational principle in quantum mechanics is based on a very simple theorem. And the theorem is as follows. For any normalized wave function psi, we have this result, that the expectation value of the Hamiltonian for a system using that particular wave function psi must not be less than the ground state energy of the system. In other words, the expectation value bra psi, H operator ket psi is greater than or equal to E0, where E0 is the ground state energy. Now this is a theorem, of course, and it requires a proof. The proof actually is simplicity itself. Note that we can write the ket psi, an arbitrary ket psi, as a superposition of the eigenkets of the Hamiltonian phi 0, phi 1, phi 2, phi 3 and so on. So here the phi n's are eigenkets of the Hamiltonian, that is, if you apply H on the Hamiltonian, you get En, the eigenvalue corresponding to the nth eigenket, times phi n. And these eigenkets, of course, have this very familiar property that phi m, phi n, the overlap is delta mn, that is, the states are normalized. Of course, we also know that the En's are real, and for the time being, we are going to assume for simplicity that the eigenvalues are discrete and they form a sequence E0, E1, E2 and so on, where E0 is the lowest energy eigenvalue, E1, E2, E3 keep on increasing in succession. The normalization condition on the eigenkets phi m's and the fact that the ket psi is normalized leads us very simply to this result, which I'm pretty sure all of you are very familiar with. And you all know that this allows us to interpret the Cn mod square quantities as probabilities of finding the system in the state phi n if you know that it's in the state psi. And I'm pretty sure all of you are also aware of this very simple result, that the expectation value of the Hamiltonian given this kind of expansion of psi is simply given by Cn mod square En. The simple interpretation of this, of course, is that the Cn mod square gives you the probability of finding the result En when you measure the energy, given that you know the system is in the state psi. And so the expectation value is, of course, the weighted average of the energies and is given by a quantity like this. Now, since Ens are all greater than or equal to E0, E0, remember, is the lowest energy eigenvalue. If you replace all the Ens by E0, the result can only go down, never go up. So you have this inequality. Cn mod square En sum is greater than or equal to Cn mod square E0 sum. Note that you can have an equal to sign here simply because it's possible that your sum is such that only C0 mod square is non-zero and all the others are 0. Of course, in that case, C0 mod square has to be 1 because this condition has to be satisfied. Now, in any case, once you have seen that this quantity is a lower bound for the expectation value of H, it's easy to see that E0 being a constant can move out of the sum, leaving you with this sum, which is 1. So this term here is actually equal to E0. So what this proves is our result, that the expectation value of a Hamiltonian in an arbitrary normalized ket is always bounded below by E0. It can go as far down as E0 but no further down. This principle gives us a procedure which we can follow to try to estimate the ground state energy of a given system. For this, what we do is we choose a family of trial wave functions, psi, with argument q, which stands for coordinates, could be just a single x coordinate or could be r vector, could be r theta phi, whatever. So these q's are just the coordinates, along with a bunch of parameters. So psi is parameterized not only by the coordinates but also by a bunch of parameters which I have written symbolically as beta within a curly bracket to indicate that this could be a set. So beta stands for one or more parameters that we can vary. Okay, so this is my family of so-called trial wave functions. Now, using this family of trial wave functions, we can calculate the expectation value of the Hamiltonian. And the expectation value, of course, will depend on the parameters beta. And this is what I call curly E of beta. This, remember, is not the energy eigenvalue of the system in general. This is just the expectation value calculated within this family of trial wave functions. And of course, as you vary the wave function within the trial set by varying the parameters, the expectation value is going to vary. But remember, the expectation value will always be greater than or equal to E0. That was our variational principle. And now, what we can always do is look for the minimum value which curly E of beta takes within this family. That is, we vary beta and minimize curly E of beta with respect to it. And this lowest possible value of curly E of beta within the family we have chosen gives us an estimation or approximation for E0. This is what we call E0 variational, and we know that this E0 variational, even the lowest value, has to be greater than or equal to E0. Of course, within the family that we have chosen, E0 variational, the minimum value of curly E of beta is going to be the closest that we can get to E0. Now, let me warn you that the variational principle only guarantees that E0 variational is greater than or equal to E0. It does not tell you by how much it exceeds E0. So, if you choose your family of trial wave functions badly, it's very possible that E0 variational will be much bigger than E0. maybe even bigger than, say, the 10th excited state energy. Or, well, 10 is just a number, could be bigger than any excited state energy that you can think about. However, if you were to judiciously choose your family of trial wave functions, you should be able to get pretty close to E0. So in a sense, applying the variational principle is both science and a bit of an art. The art lies in deciding from the basic properties of the system what kind of wave function best describes the ground state. And you have to choose your trial set of wave functions to at least try to mimic most of its properties. As you will see later, there are some methods by which we can also find a lower bound on E0. Since E0 variational gives you an upper bound, it's possible now to know a range within which E0 lies. And if we can choose our trial set of wave functions judiciously enough and use the method for finding the lower bound, well, again judiciously enough, we may be able to sandwich our value of E0 between two bounds which are rather tight. And that will give us a rather good estimate for the ground state energy. Now, while our formulation for the variational principle has focused on the ground state energy and determination of the ground state energy, or at least estimation of the ground state energy, is one of the major applications of the variational principle, it is also possible to modify this so that we can find an estimate for higher energy eigenstates as well. Well, for this, let me point out that if you choose your eigenket expansion psi in such a way that while it's expanded in terms of the eigenkets, the expansion goes from n equal to 1 to all higher values, that is n equal to 0 is excluded, or otherwise C0 is 0, then the expectation value of H must be bounded below by E1. E0 is still of course a lower bound, but now if your eigenket obeys C0 is 0, then the lower bound actually can be improved to E1. Of course, if you could make both C0 and C1 0, then the lower bound would be E2. Of course, if you want to use the variational principle to estimate, say, the third excited energy eigenstate, then you have to ensure that every wave function in your trial family of wave functions is orthogonal simultaneously to the ground state, the first excited state, and the second excited state. Now, while it is possible under some special situations to do this, we usually focus on finding out the ground state energy and perhaps the first excited state energy using the variational method. As I have said, to estimate the first excited state energy, what you have to do is to ensure that your trial set of wave functions contain only wave functions which are orthogonal to the ground state. Now, how can you achieve that? There are several possibilities. One of them is a situation where the ground state wave function may be exactly known, so that this gives you a condition on your trial set of wave functions which you can use to ensure that all your trial wave functions are orthogonal to the ground state. There are situations where the ground state wave function may not be exactly known, but may have some well-determined symmetry property, which allows you to ensure that your trial wave functions are all orthogonal to the ground state, even if you don't know the ground state exactly. An example of this, say, would be the case of potentials in one dimension which obeys V minus x equals Vx. Remember, we had established earlier that the bound state wave functions for such a system must be even and odd, and the ground state must be even because it has to be nodeless, and the first excited state must be an odd function. So if you choose your trial set of wave functions to constitute odd wave functions only, then by default they are all going to be orthogonal to the ground state wave function, simply because of the very simple mathematical result from class 11 or 12 that the integral between symmetric limits of an odd function always vanishes. And finally, and this is the most common scenario, you may not exactly know the ground state wave function, You may not even have a symmetry property which helps you out here. But it's quite possible that you have used some method, perhaps even the variational method, to estimate the ground state wave function, and then you ensure at least that your trial set of wave functions are all orthonormal to this ground state wave function approximation that you have. Of course, as you must realize that this is going to be somewhat error prone, and doing it for higher energy eigenstates are going to be even worse in such situations. So this is the reason why estimating higher and higher energy eigenstates using the variational principle is not such a great idea. We mostly focus on the ground state and at best some of the lowest excited energy eigenstates using this method. However, the ground state of a system is a very, very important feature of the system, and so the variational principle happens to be very useful, even if it just gives me a good estimate for that. Let us now first see a few examples of the variational principle in action. We will begin with the Hamiltonian, which is very familiar to all of you. In fact, it is one of the best known Hamiltonians in quantum mechanics. The Hamiltonian for the simple harmonic oscillator. Now, we have made life simpler for ourselves by choosing special units so that h cross, m and omega, the parameters which appear in the Hamiltonian, are all set equal to 1. So the Hamiltonian looks like minus half d2 dx2 plus half x square. Of course, we actually have the advantage that we know all the energy eigenvalues and eigenfunctions for this exactly. So in a sense, it's useless to use the variational principle here, since the exact solutions are already known. However, one of the major reasons why we focus on the harmonic oscillator in here is that this will give us confidence in how good our results are going to be using the variational method, simply because we know what the exact results are and we can see how well or how badly we can approach the ground state energy eigenvalue using the various trial set of wave functions that we will use. Now, of course, we know that the energy eigenvalues for this particular Hamiltonian is h cross omega into n plus half, but given our choice of units, we are going to get n plus half only, h cross and omega being 1, and the ground state energy eigenvalue will definitely come out to be half. That's the exact result. Let us see what variational principle will tell us. Of course, for the variational principle to work, we need to start with a family of trial wave functions. And this family cannot be chosen completely arbitrarily. Remember, the closer you get to the physics of the system, the better your estimation is going to be. Here at least we expect several important things. We expect that the wave function should die out in infinity. We expect the ground state wave function to be nodeless. Also, because the system is parity symmetric, we expect the ground state wave function to be an even function. Now, coupling all these features together, we can come up with a trial family of wave functions which are simply normalized Gaussian wave functions. So, psi of x comma alpha is 4th root of alpha by pi e to the minus alpha x square by 2. The 4th root of alpha by pi simply arises because of the Gaussian integral of e to the minus alpha x square, which is what you need because you need to integrate psi x mod alpha mod square from minus infinity to plus infinity, gives you root over pi by alpha, as you all know. Of course, for this wave function to be normalizable and at all behave like a decent wave function, the parameter alpha has to be positive. Now, if you start with a normalized set of Gaussians, the advantage is that you can exactly calculate the expectation values involved rather simply. For the ease of discussion, we are going to break up our calculation into several steps. What we need is the expectation value of the Hamiltonian, but we will calculate the expectation value of the kinetic energy and the expectation value of the potential energy separately and then add them together to get our curly E of alpha. Now, Expression value of the kinetic energy, of course, is nothing but the integral of psi star x alpha followed by the kinetic energy operator acting on psi x alpha. The kinetic energy operator, which is minus h cross square by twice m d2 dx2 in general for one-dimensional systems. Here it is simply minus half d2 dx2. Again, our choice of unit simplifying this thing a bit for us. Now, let me introduce to you one result which is actually going to be very useful, especially in one-dimensional calculations. In order to evaluate this particular integral, you actually need to differentiate the function twice and then multiply by the complex conjugate of the wave function. Now, because the I d dx or 1 by I d dx is a Hermitian operator, that's a momentum operator, and this is the square of the momentum operator, you can easily see that this result works. What you need is psi p square psi expectation value, but that actually is p psi wave function's norm. That's simply the Hermitianity of p. So what is possible is that instead of differentiating the wave function twice and then multiplying by psi and integrating, you could also simply differentiate it once, take the mod square of that and integrate. The half is of course just this half which is coming out. Of course you had a 1 by I here if you were thinking in terms of the momentum operator, but 1 by I mod square of course is 1, so that can be just simply forgotten about. Well, you don't really have to use the Hermitianity of the momentum operator here. All you could do is just integrate this by parts and insist that the wave function dies out fast enough at infinity for the integrated out part to vanish, and that will still give you this equation. The fact that the integrated out part vanishes is exactly what is responsible for P being Hermitian in the first place. So basically that's the same thing thought about in perhaps more elementary language. Now for this integral, what we need is to differentiate d psi dx once. D psi dx's differentiation, of course, is simply minus alpha x times into the minus alpha x square by 2. You are squaring that, so you get alpha squared x square into the minus alpha x square, and that's what you need to integrate. So basically you need to integrate a Gaussian function times x square. Now, we already know that this is the integral that we have. Of course, the integral that we need is x squared times into the minus alpha x squared. And as you are all aware, you can easily evaluate this by converting this integral to a gamma function simply by substituting alpha x squared equals t. Well, hold on, you can't really substitute alpha x squared equals t. That's a bad substitution to make. Remember, over the interval minus infinity to plus infinity, alpha x squared is not a one-to-one function of x. Negative x values give you the same result as positive x values. So this substitution really cannot be done. But you all know how to handle that. You use the fact that this integrand is symmetric to actually convert this to an integral from 0 to infinity and then substitute alpha x squared equals t, because that of course is a range over which the map alpha x squared goes to t is 1 to 1, and that converts this to a gamma function. This one will become gamma half, the next one will become gamma 3 by 2 and so on, and using that you can easily find out the values of the integrals. Now, apart from the gamma function approach to finding out the values of these integrals, there is another one which is actually quite cute. I'm sure most of you already know about it, but just for the sake of those who don't, let me show you another way of evaluating the integrals, which are the integrals of various even powers of x times e to the minus alpha x square, using what I am calling a cute method. The cute method essentially is the following. Note that both sides of the equation depend on the parameter alpha. Of course, the integrand here also depends on x, but once you integrate over x, the result only depends on alpha. So what we can do is do a dd alpha on both sides. You can differentiate both sides of this expression with respect to alpha. Now this dd alpha can travel inside the integral And that is what is called differentiation under the integral sign. But once it goes in, it becomes del alpha. So you do a partial derivative of the integrand with respect to alpha, keeping x constant. It is easy to see that once you do that, what you end up with is minus x square e to the minus alpha x square dx on the left. The right hand side, of course, is just an ordinary derivative, which will be minus half root pi by alpha to the power 3 by 2. And just by cancelling out the minus on both sides, we end up with our integral x square e to the minus alpha x square dx is just half root pi by alpha to the 3 by 2. Repeating this once again will give me x of 4. Another minus sign which you can cancel on both sides is the derivative on this side, which is half times 3 by 2 from the alpha to the minus 3 by 2 root pi by alpha to the 5 by 2. And of course, if you were to integrate x of 6 into the minus alpha x square dx, you would get half into 3 by 2 into 5 by 2 root pi by alpha to the 7 by 2 and so on. It of course does not matter whether you use the gamma function approach to evaluate the integrals involved or you use this cute differentiation under the integral sign method. What matters is that all the integrals necessary for this calculation can be exactly evaluated. So let us get back to the task of evaluating the expectation value of the kinetic energy operator, which essentially is the integral that you see here, and as we said is really the integral of this quantity alpha square x square e to the minus alpha x square dx, and half times root over alpha by pi, which comes from the normalization squared, is sitting outside. The half is of course this half. So we just use the value for x square to the minus alpha x square that we had just calculated, plug it in, and it's a matter of very simple algebra to find out that the result is going to be alpha by 4. We can repeat essentially the same calculation for the expectation value of V alpha, where it's just psi mod square times half x square integral. You actually end up with exactly the same integral to calculate, but because of the prefactors being slightly different, you end up with a similar but not identical answer. You get 1 by 4 times 1 by alpha. Putting these two together, we see that the expectation value of the energy in the state curly E of alpha is simply 1/4 alpha plus 1 by alpha. What we now need to do to estimate the best possible value of the ground state energy staying within this trial set of wave functions is to minimize this expression of E alpha with respect to alpha. Now you could of course use calculus to find this, that is, you could differentiate this with respect to alpha and then set alpha equal to 0 and check whether what you have got, this extremum, is actually a minimum. But there's a very easy way of doing this using basic algebra. And so let me just point out that all you have to do is complete the square in this fashion. And this tells you that the minimum possible value for this expression is going to be 2 by 4, that is 1 by 2. That will happen when alpha is equal to exactly 1, so that the square vanishes. So the minimum value of E alpha, which is our variational estimate for the ground state energy E0 variational, comes out to be half. And the wave function within our trial family of wave functions which achieve this minimum is in a sense the closest we can get within our trial set of wave functions to the ground state wave function, is given by 1 by root over 4th root of pi e to the minus x square by 2, simply by putting in alpha equal to 1. Note that this is actually an exact result. The ground state energy is exactly half, and if you have managed to get half, the only possible way you can get that is that your trial wave function has actually hit upon the exact wave function. Remember, what we had is this result that expectation value of h is greater Cn mod square En, that's greater than equal to E0, and the only way in which this can be an equality is C0 mod square is 1 and all the other Cn mod squares are 0, which means your state ket psi is actually exactly the ground state ket, phi 0. Now it's very easy to see why we have found the exact result here. In this particularly simple problem, we knew the exact solutions and we knew that the ground state wave function is a Gaussian. So if we take a family of trial wave functions which constitute of the Gaussians, there is one wave function among all of those, the one precisely for alpha equals 1, which exactly matches the ground state wave function. So it's not a surprise that we have managed to get an exact result here. In a more general problem, we will of course not be so lucky. We will not be able to find a trial set of wave functions in which somehow miraculously our exact energy eigenfunction is already there. So at best what we can hope for in general is to choose my trial set of wave functions in such a way that they mimic our ground state wave function rather well, so that we can get a good estimate of E0. The fact that you get an exact result here is a bit of a fluke, but it's also easy to understand. While we pretended that we don't know the solution and hence we are trying a variational method, we actually knew the solution and we chose our trial set of wave functions accordingly. Just to see what happens when we choose a different trial set of wave functions, we are going to solve the same problem again using a different set this time. Note that whatever wave function we choose, we must insist that the wave functions die out at infinity. And another function which does that is e to the minus alpha mod x. Note the mod x is essential because you want it to die out both at plus infinity and minus infinity, and of course alpha has to be positive for that to happen. And the normalization factor root alpha here is very easy to figure out using elementary integrals. Now the calculations for the kinetic energy and the potential energy expectation values here is rather simple. Just one word of warning here though. Trying to differentiate this wave function twice will lead to trouble because you are going to get a delta function like singularity at x equal to 0. That's really not too much of a trouble. You can actually use both d2 psi dx2 times psi stars integral, treating the delta function that you get carefully to get the result for expression value of t, or you could use d psi dx mod squares integral, which will avoid this infinite singularity in the first place. In either case, the integrals involved are really very simple and you end up with alpha square by 2 for expression value of t and 1 by 4 alpha square for the expectation value of v. So now with this trial set of wave functions, the expectation value of h turns out to be half alpha square plus 1 by 2 alpha square. Rather similar to what we had before, and we can easily extremize this by either by using calculus or by using exactly the kind of method that we showed, the algebraic method that we used in the last case. But the estimate that this gives for the minimum value of energy, and this is what you need to verify for yourself, happens to be 1 by root 2. So that's the minimum possible value which expectation value of h will take as you vary alpha. And this 1 by root 2 of course is around 0.7. And since the exact value for the ground state energy is 0.5, this is really not that great an estimate, but not very bad either, given the fact that the wave function we have chosen, which looks something like this, of course it's even, so it doesn't really look like the nasty wave function that I have drawn, but you get the idea. It's really rather different from the Gaussian kind of wave function that the actual exact energy eigenfunction has. Is given that, it's rather good that we have been able to get this close. Now, so far we have been dealing with cases which have only one parameter to vary. But if you had more parameters to vary, it gives you more freedom, and it's easy to understand that you may be able to get better results using that. So let us continue with the pretense that we do not know the exact solution for the ground state of the harmonic oscillator, and let's try to build a new set of trial wave functions which have more than one parameter. And we are going to essentially build up upon what we have here, this e to the minus alpha mod x kind of wave function, and modify it by introducing a prefactor which is a polynomial. Note that the e to the minus alpha mod x is doing the job of making the wave function die out at infinity. The polynomial factor which I have chosen in the front has been chosen carefully to be an even function. We already know that our system is paired symmetric, and we know that the ground state has to be an even function, which is why I did not bother to put in a 1 plus beta x term. You can check what happens if you include the 1 plus beta x term, and note that you will not really get an improvement over your previous result in such a case. However, let me also point out that this wave function has not been normalized. So when you calculate the expression value of the energy, the calculation will have to involve both the normalization and calculating the integrals involved. This is a rather involved but somewhat straightforward calculation. It just takes a lot of time to carry it out. If you actually carried it out, you would end up with this rather horrible looking expression for curly E of alpha and beta. And your job now would be to vary alpha and beta in such a way that you would get a minimum for this curly E. Now, while the integrals involved in this calculation, though lengthy, can be carried out using elementary methods, just takes some amount of time to calculate the whole thing out. Finding out the minimum for this two variable function is really rather difficult. So what we will do is we will explain how to do this using the standard softwares that are available to us, in particular using scipy's optimize module. If you want to make use of the optimize module, of course you must have Python, NumPy and scipy installed in either your laptop or your smartphone. You will be able to follow what I am going to say next even without the installation, but it's much more fun to be able to do it yourself. So now is a good time to get it installed if you haven't done it already. It's freely available and you can easily download the required stuff. So first step in optimizing a function like this using the optimize module is of course to import the optimize module. So I'm just going to show you a code snippet here. You import scipy.optimize. I'm just opting to call it opt. So I'm importing scipy.optimize as opt so that later on I can just refer to contents of the scipy.optimize module using this shortened word opt. The next step is to define our function which we want to extremize. So this function has to be a function of a single NumPy array or a list. X contains the two quantities that we want, alpha and beta. Of course, we don't call them alpha and beta here. We're just calling them A and B. So what we are doing here is that the function takes X as an argument, splits it up, technically unpacks them into two variables A and B, and then returns the value of this function which has been calculated. This is exactly the function which is sitting up here. Twice alpha to the 4 plus 4 times alpha to the 8 and so on. So once you have this function defined, you're ready to go. What you need to do is call this opt.minimize function. It's actually the minimize function from the scipy.optimize module. But because I'm calling scipy.optimize opt here, all I have to call is opt.minimize and give the function that you want to minimize, in this case the function that we have called E, followed by a guess value of the argument that minimizes it. Remember here the argument is a two element array or list. I'm giving a list with A and B both starting out at the values of 1 and 1 each. Okay. Now this produces a rather long output which you can see out here. But what is of interest to us right now is the first line of the output and the very last line. The data in between is actually quite important, and if you want to understand exactly what all of these things mean, what you need to do is take a look at the documentation which is available online. But what is important is that this is telling us what the minimum value for the function that it has achieved is. It's saying that the minimum it has achieved is 0.7374, etc. And that has happened at this, what this last line is saying, at the value of x. Remember A and B. given by 2.59 for A and 9.25 for B. Now this should be very, very disappointing. Note that without the beta at all, we had already done the calculation and found that the minimum energy that we arrive at is around 0.7, 1 by root 2. This is giving me a larger value for the minimum, and given the fact that beta equal to 0 is very much a possibility within our family of wave functions, that is, the previous family, which had only e to the minus alpha mod x and a normalization, is very much contained within this particular family. It stands to reason that whatever minimum I get from here can only be lower than the minimum I had before, cannot be higher, but yet my optimized function is actually giving me a value which is higher than 0.7. Now what does it mean? It means that what it has done here is that it has managed to find a minimum, or at least something which is close enough to a minimum, but it's not necessarily the global minimum that you are looking for. The way these optimization programs work is roughly as follows. It starts at whatever trial value you are giving and then tries to adjust the parameters in such a way that the function to be optimized goes towards its goal. In this case, it goes lower because you want to minimize it. And once it stops going lower by a preset amount, it stops there and says that I have found the minimum. That's an oversimplification. It's really much more complicated than that and much more sophisticated than that. But that sort of gives you the idea of what's going on. So what might happen is that the system may get trapped into a false minimum, and that is exactly what has happened here. Thankfully, in this case, we already know that this result cannot be the absolute global minimum for this function, because we already know that when beta is 0, the minimum that is achieved by varying just alpha is around 0.7. So we should not be fooled by the result which the program has thrown at us. But notice that we are getting this result because we have started with alpha equal to 1 and beta equal to 1. Maybe a much better idea would be to start at alpha equal to 1 and beta equal to 0. Well, just to show that it will work in this case, let's start with alpha equal to 1 and beta equal to 0, which is exactly the situation that we did the previous calculation from. And if you do that, you do get to a minimum value. In fact, this value is the global minimum. You get 0.642, which is an improvement over 0.7. Remember, any value which goes lower is an improvement because it's going to get you closer and closer to the ground state energy eigenfunction. Since the ground state energy value is a bound, you cannot go below that. So, any value which takes you lower gets you closer to it. And alpha and beta, these are the values of alpha and beta that you need to actually get to this minimum. So, even when you are using a sophisticated optimization module like this, it is important to know exactly what you are doing. You can't just use numerical methods or software packages blindly. All this is nice and well, but it actually runs the risk of making you think that the only system we can solve using the variational method is the harmonic oscillator. Of course, for the harmonic oscillator, approximation methods are not really necessary because we know the exact solutions there. Just to see how you could use this for a system where we do not know the exact answer, let us consider an harmonic oscillator next, the quartic oscillator. So this is a non-trivial problem where the Hamiltonian is given by minus half d2 dx2. We are still going with for the units where h cross m are all 1 plus x to the 4 by 2. So we are using a dimensionless x here as we did in the previous example. Now we use, just for simplicity, the same trial family of wave functions that gave us wonderfully good results for the harmonic oscillator case, in fact gave you the exact result, the normalized Gaussians. One reason for choosing normalized Gaussians is that we know how to calculate the integrals exactly in that case. Also, because we do expect our wave function to be somewhat close to a normalized Gaussian, something which will die out in eternity and be smooth throughout and so on. It's very easy to calculate the expectation value of t and v. In this case, all you have to do is follow the standard Gaussian integrals that we wrote down, and you will get these expressions: alpha by 4 for kinetic energy expectation value, and 3 by 8 alpha square for the potential energy expectation value. The expectation value for the energy curly E of alpha works out to be 3 by 8 alpha square plus alpha by 4. And to minimize this, what we need to do is differentiate with respect to alpha and then set that equal to 0. And it's pretty straightforward to see that the result that you get is alpha naught works out to be cube root of 3 in this case. If you plug the value cube root of 3 back in the expression for curly E of alpha, you get the variational estimate for the ground state energy here, which turns out to be 3/8 of cube root of 3, and that is close to 0.5408. 0.54, slightly more than the ground state energy eigenvalue for the corresponding harmonic oscillator. Now the question is, how good is the variational estimate in general? We did get a value 0.54 in the last problem, but do we really know whether it's any good, or is it really just some upper bound? The actual value may be much lower. Now the variational method gives upper bounds for the energy levels, but does not say how tight the bound is. In principle, the ground state energy could be anything below 0.54. Of course, here, since the potential energy is throughout positive, we know that the ground state energy has to be positive. So we know that it's somewhere between 0 and 0.54. But just from this, we have no real way of knowing how close to 0.54 this is. Of course, given the fact that we have used a wave function which should be reasonably good in mimicking the property of my system, I am reasonably confident that the value of 0.54 is not too far away, not too much higher than the ground state energy actually. However, just from the variational principle, there is no real way of knowing how much higher we are. Now, of course, as I have been saying, if you choose a family of wave functions that capture the essential features of the physical system, that helps us in getting better results. And it is because of this, you need to use your physical understanding of the system and not just blind mathematics in order to apply variational methods successfully. Now, if you can find a lower bound, that can help in sandwiching the estimate. So if in addition to the upper bound that your variational estimate gives you, if you also can find a lower bound, then you will be able to sandwich your ground state value in between the two. Now, there are techniques by which you can find a lower bound, and I'm going to explain one of them to you in this lecture. We will see ways of improving upon this in a subsequent lecture. Now, an approach which helps us find the lower bound can go like this. It starts with the variance of the Hamiltonian. That is, you find the squared deviation of the Hamiltonian from the expectation value of the Hamiltonian and take its expectation value. This is a very, very familiar quantity. You also, of course, know this as delta H whole squared. And you all know this very important result, that this is the expectation value of H square minus the squared expectation value of H. And for later reference, I'm going to call these two quantities capital D of psi, and of course this expectation value already is curly E of psi, and the square of that is sitting here. And you all know that this quantity has to be non-negative, simply because H being a Hermitian operator, H minus expectation value of H is also a Hermitian operator, so a square is a positive definite operator. Now, is this bound on sigma, that sigma has to be non-negative, which helps us to find a lower limit to some energy eigenvalues. So how does this work? We can of course use the eigenfunction expansion to write sigma in this form. Sigma is simply the weighted average with the same probability weights Cn mod square of En, the energy eigenvalue, and curly E psi, the expectation value. So En minus E psi whole square times Cn mod square. Now, among all the energy eigenvalues E0, E1, E2, E3 and so on, one of them, let's say Ek, will be closest to the value of curly E psi that you have calculated. Of course, if our family of wave functions that we have taken is a decent good family, then we expect this Ek to be E0, but we cannot really be sure of that. If we have chosen a trial set of wave functions which is very far away from what the ground state wave function looks like, the closest energy eigenvalue could be some excited energy state. But there has to be at least one Ek which is closest, and if we use that, we use the fact that for all the energy eigenvalues, as n runs over all possible values, Ek minus E psi whole square is definitely less than or equal to En minus E psi whole square. That's what being closest really means. Remember, it's the square which actually obeys this inequality, because it's possible that Ek could be below the energy expectation value that you have calculated, or could be above it. So I'm not very sure whether Ek minus curly E psi is positive or negative, but we do know its square is definitely positive and it's less than or equal to En minus E psi for all n. Equality, of course, holding for k equal to n. And if you use that and use a calculation which is very similar to the way in which we arrived at our variational principle, we find that sigma is bounded below by Ek minus E psi whole square. So, the deviation of the closest energy eigenvalue from curly E psi is bounded. Its square cannot exceed sigma. And what that means is that Ek lies between E psi minus root sigma and E psi plus root sigma. And this guarantees that once E psi is found, there is at least one energy eigenvalue in the interval E psi minus root sigma to E psi plus root sigma. And if we have not been too bad in choosing our trial wave functions, then E0 is between E psi minus root sigma and E psi plus root sigma. You already know that E0 has to be less than or equal to E psi. So it's actually between E psi minus root sigma and E psi. However, that of course presupposes that you have been good enough in choosing your trial set of wave functions so that E0 is the one which is closest to curly E of psi. In an unknown system, that may not always be the case. To see whether this is any good, let us go back to our Qatic oscillator. With the same trial family of wave functions that we had used, the normalized Gaussians, the calculation gets a bit lengthier at this stage, and I'm just going to quote the results for you. Let me point out that though the calculations are lengthier, they are actually well within tractable limits and can be done rather easily. It's just that it takes a bit more time. The expectation value of h square turns out to be this expression, and if you calculate sigma from here, which is of course expectation value of h square minus expectation value of h whole square, this quantity we have already calculated when we were estimating the ground state energy for the Qatic oscillator, it turns out to be this rather simple looking expression. Now, at the value of cube root of 3 for alpha, which remember is the one which gives you the best possible estimate for the ground state energy, square root of sigma, when you plug it in here, ends up being around 0.294. So using the fact that we know that there is an energy eigenvalue between curly E psi minus root sigma and curly E psi plus root sigma, this tells us that there is an energy eigenvalue between 0.246 and 0.835. Can we use this to say that the ground state energy is between 0.246 and 0.541, which is the upper bound we had found for the ground state energy a while ago? Strictly speaking, we can't. We should be reasonably confident that this is true. But strictly speaking, it's possible that the ground state energy is somewhere even below 0.246. But what this is telling you is that there is guaranteed to be at least one energy eigenvalue, maybe the first excited state, between 0.246 and 0.835. We will see later that actually 0.541 is a pretty good result, but in order to see that it's a pretty good result, we need to be able to find a better lower bound for the ground state energy and be sure that it is a bound for the ground state energy. Note that this calculation for sigma just tells us that there is one energy eigenvalue in between the interval. We are reasonably confident, given the nature of the wave function we have taken, a nodeless function which dies out at infinity, that what we have got is a decent estimate for the ground state. But to be sure, we need to sandwich the ground state energy better using a tighter lower bound. In the next lecture, we are going to describe a rather interesting method for finding out a tighter lower bound on E0. This is due to somebody called George Temple, who derived this somewhere around late 1920s. So this is almost as old as quantum mechanics is. In fact, when he first derived it, he was actually using the variational principle as it is used in continuum mechanics, not in quantum mechanics, but in the theory of fluids. But he saw that he could also use it for quantum mechanics. And as it turns out, it happens to be one of the best methods that we have for finding a tight lower bound. But that is for the next lecture. Until then, goodbye.